This is the first lesson in the logarithmic functions unit. In this lesson, we are going to start by comparing and contrasting the exponential function with the logarithmic function, and in doing so, explain how the logarithmic function is the inverse of the exponential function, and then define a logarithm and perform simple logarithm calculations. So last year, you learned about the exponential function, and the exponential function was this. It was f at x is equal to a to the power of x, where a is your base, and it had to be greater than 1 but not equal, greater than 0 but not equal to 1. So let's look at two exponential functions. Let's just look at a basic exponential function right here. F at x is equal to the base a raised to the power of x. So if we're looking at this graph right here, we have a number of key features. Well, the first key feature is this key point right here, which is your y-intercept. And so your y-intercept there was 0, 1. And the reason for that is because any base raised to the power of 0 is going to be equal to 1. So that point is always going to be on an exponential function graph, provided that there is no transformations. If we look at the increasing or decreasing intervals of this graph right here, we can see that this graph is strictly increasing. So we'll write that in, strictly increasing. We can see that there is an asymptote at y is equal to 0. And that's because as x gets increasingly small, this becomes a smaller and smaller fraction. All right? And we can see that just by doing a few examples. Say we had 2 to the power of negative 1. Well, that's 1 over 2. 2 to the power of negative 2 is 1 over 4. 2 to the power of negative 3 is 1 over 8. And 2 to the power of negative 4 is equal to 1 over 16. So we can see that as x gets increasingly small and negative, we get smaller and smaller fractions. The domain for this graph is x is an element of all real numbers. The range for this graph is y is an element of all real numbers such that y is greater than 0. Just scroll down so you can see that. There you go. We can also look at this graph right here, and this is simply the graph of f at x is equal to 1 over a to the x. Okay? So pretty similar to this one, just that the base is the reciprocal of this base over here. So we had a over here, and now we have 1 over a to the x. See if you can come up with the key points, increasing and decreasing intervals, asymptotes, domain, and range for this graph right here. Okay, so hopefully you're able to see that, again, we have the same key point, the y-intercept right here, and that is because, again, if you had 1 over a to the power of 0, so if we set x equal to 0, 1 over a to the power of 0 is equal to 1 because of the zero power law. Anything raised to the power of 0 is equal to 1. This one graph will be strictly decreasing. It has the same asymptote and the same domain and range as its graph with just a to the power of x. Okay, let's take a look at inverse functions. We're going to review this. Hopefully you saw this last year in MCR3U. The inverse of a function is when reverse operations are performed to undo the operations of the original function. So we'll take a basic example here, 2x plus 1. This is a linear example, right? And see if we can list the operations on x, then reverse or undo them to find the inverse. Right, so what are the f of x operations on x? When we input x into this function, what happens? Okay, so we start with our x, we input it into the function here, and we can see that it is multiplied by 2. Okay, so it gets multiplied first by 2, and we get 2x. Then we can see that that product is then, we add 1 to that product. And we get 2x plus 1, right? So we have two operations on x. First, we multiply by 2, then we added 1 to end up with our function. Now, again, if we've defined the inverse of a function to be the reversal of those operations, then we would have to start with x, and we'd have to go in backwards order. So we would have to undo both of these operations. And so we start undoing these operations by, instead of adding 1, we're going to subtract 1. And we would have x minus 1. We're going to go backwards from here. Then, instead of multiplying by 2, we're going to divide by 2. So we would have, divide by 2, x minus 1 all over 2. And then we would say that the inverse of x is x minus 1 all over 2. We can also achieve this algebraically by switching the x and y values of the original function. So I'll write the original function in blue here, and I'll say that if f of x is equal to y, so we just say y is equal to 2x plus 1, to find the inverse, we switch the x and the y values. So we would have x is equal to 2y plus 1. Then we're going to take 1 away from both sides, so we would have x minus 1 is equal to 2y. And then we would divide both sides by 2, and we would end up with this, right? So we would say, therefore, f inverse of x, the inverse operations that are undoing the original operations of the function, is defined as follows. So we can also see this on a graph. If we had a parabola or a quadratic function as our original function, these are the points on the original parabola. These are the points on the inverse of that parabola. So f inverse of x is equal to the plus or minus square root of x. I want you to take a look at the x and y values of the original function, and then look at the x and y values of the inverse function. I want you to see if you can notice anything between the x and y values of the original function and the x and y values of the inverse function. Just pause the video and see if you can come up with it. Okay, hopefully you were able to see that the x and y values of the original function are switched with the x and y values of the inverse function. And we can also see that the original function is then reflected in the line y is equal to x right there. So another way of seeing the inverse of a function graphically in comparison to its original function. Okay, so the key thing here to remember is that the x and y values are switched. So the reason why we've taken some time to discuss inverse operations is because logarithms are simply the inverse of the exponential function. So let's take a look at our exponential function operations. You input the x value, which is the exponent, and then it outputs the base raised to that exponent. So you input the exponent, and it outputs the number of the base raised to that exponent. If we were to undo or reverse that operation, so we're inputting an exponent and it outputs the product, the reverse operation is as follows. You input a number and it outputs the exponent on the base that produced that number. That's what a logarithm is. Okay. In the exponential function, you input the exponent. The logarithmic function outputs the exponent. So it's just the reverse operation of the exponential function. So we define that as g at x is equal to log x with base b. The log x with base b. So this small number is the original base, and this is what the number is raised to that exponent, or raised to the exponent. If b is not given, then we assume that it is 10. We'll probably see, you'll probably understand this a little better if we do a few examples here. So let's try some examples. Evaluate the following logarithms. Remember, the logarithm returns the value of the exponent that produced the number x. Okay, so if we look at log 4 base 2 right here, we have to think, okay, this is going to return the exponent on 2 that produced 4. This is what you should be thinking in your head. Log 4 base 2. Okay, so what is the exponent on 2 that produces 4? Well, the exponent on 2 that produced 4 is just 2. Let's look at the next example. Log 1/9 base 3. So I have to think, what is the exponent on 3 that would cause that to become 1/9? All right, well, if I think about that, I know that 9 is basically 3 squared, but this right here is 1/3 squared, so that means that it was likely 3 to the power of -2. So log 1/9 base 3 is equal to -2. Again, you have to remember that the log will return the value of the exponent right there. Let's keep going over here. If you have to pause the video at any time to copy the note, just pause it, copy the note, and then keep going. So over here we don't have a base, right? And it says if b is not given, it's assumed to be 10, which is called the common logarithm. So this right here, we know that the base is 10 because it's not provided. So we have to think, 10 to what exponent is equal to produces 1000? So what is the value of the exponent? That's what's going over here. That's what the logarithm returns. What is the value of that exponent? Well, 10 to what power produces 1000? Well, that's 3. The value of the exponent there is 3. Looking at the next example, again, log 1 base 2. Well, again, I have to think 2 to what exponent produces 1? What would the exponent be on 2 that causes it to become 1? Well, remember, anything raised to the power of 0 is 1, so the value of this logarithm is simply 0. All right, instead of dealing with numbers, we're going to have a few examples here that involve variables. So log x base x. So same idea as above. We say, okay, we have a base x raised to some exponent produces just x. So what is that exponent? X raised to what exponent just gives us back x? 1. So the answer here would be 1. This one right here looks more complicated than it actually is. Log 2 to the power 5 base 2. We have to think in our heads, okay, the base is 2, so I'm going to put 2 here. And remember, the logarithm's returning the exponent, so that's what I don't know. So log 2 to the power 5 base 2 is saying, what is the exponent on 2 that would produce 2 to the 5? Well, that should be fairly intuitive because this would have to be the same number, right? 2 to what power equals 2 to the 5? Well, it has to be 5. Okay, we keep going. Log x to the power of 21 base x. Same idea here. X to some exponent produces x to the 21. All right, this has to be the same thing, right? If this is an equation, then this exponent has to be equal to this. So that's 21. The next one is an interesting one because we have the exponent as a logarithm. So let's just take a look at this logarithm right here and see what this comes to. Logarithm 16 or log 16 base 2. So I have to think about that. What is the exponent on 2 that would produce 16? So I'm not going to draw this out anymore. I'm just going to think in my head. What exponent on 2 produces 16? Well, 2 to the power of 4 gives me 16. Okay, so what I'm saying right here is that this logarithm right here is equal to 4. So the exponent here, so instead of writing this logarithm, I'm just going to write what it equals to. It's 4. So 2 to the power of 4, because that was my original base, and I'm just basically taking this logarithm and inserting its value back into this statement right here. Well, 2 to the power of 4 is just 16. Right? So as you can see, this returns the exponent that produces 16, and then we raise it to that exact same exponent. We just get 16 again. So it's a bit of like kind of like a circular loop there, this question right here. The logarithm right here returns the exponent on 2 that produces 16, so that's 4, and then that just becomes the exponent again on 2. So general rules for logarithm. I want you guys to actually pause this right here and see if you can come up with them one at a time. So log 1 base a. You again need to think to yourself, what is the exponent on a that would produce 1? Well, the exponent on a that produces 1 is just 0, because anything raised to the power of 0 is equal to 1. So that's your first rule. Think about this next rule. Log a base a. Again, the question you're asking yourself, what exponent on a would give me back a? And that's just 1. The next rule for logarithm. Log a to the power of x base a. And this is something that we saw over here. I'm just going to go back up here and show you. Like, look, log 2 to the 5 base 2. This is the same idea right here. Or log x to the 21 base x. So same idea. A raised to what exponent is equal to a to the x? That has to be x. And then finally, this last one over here is what we saw above. This is that kind of circular question right here where we have a logarithm of x base a, and then we're raising it to that exponent on a. So over here, what I would say here is I would say let's say that a to the y equals x. So therefore, the logarithm of logarithm x base a, right? Again, a to what power produces x? Well, we already defined that as y. So this right here, logarithm of x base a, logarithm of x base a equals to y. So we would just write this as a to the y. But we've already said that a to the y equals x. So that right there equals x. So another way of thinking about this is when you have a log x base a, this is just going to produce the exponent on a that would create the number x, and then you're raising it to that exponent. again, that's just going to be x. Answer the following questions. Does log 0 base 2 exist? Why or why not? So we have to think, what number or what exponent on 2 produces 0? This does not exist. There is no exponent on 2 that would cause it to become 0. Remember, 2 to the 0 equals 1, right? Students often want to say, oh yeah, 2 to the 0 equals 0. No, 2 to the 0 equals 1. There is no exponent that exists that will produce a value of 0. So we will write that out. Does not exist. There is no exponent will produce a value of 0. If we look at this next one, does log, again, there's a base 10 there, log negative 100 base 10? So I'm asking here, is there some exponent that would create a negative number? And again, this does not exist, right? There is no exponent produces a negative number from a positive base. Right? There's no exponent here that's going to make a negative number. Remember, if it was like 10 to the negative 2, that's just 1 over 100, which is not negative 100, right? Okay, just going to erase that. So there's no exponent that would produce a negative number, and there's no exponent that produces 0. So these don't exist. We're going to start by looking at the graph of the logarithmic function, and for that we're going to look at the exponential function, because remember what we said up here, that the logarithm is simply the inverse of the exponential function, right? Exponential function, you input the exponent and it gives you what that value is. The logarithm outputs the exponent, so it gives you back the exponent. Okay, so we put in some numbers here. So 2 to the negative 4, like this is on the exponential function, right? That's the exponential function right there. 2 to the negative 4 is 1 over 16. So I'm just going to write that in. That's 1 over 16. 2 to the negative 3 is 1 over 8. 2 to the negative 2 is 1 over 4. 2 to the negative 1 is 1 over 2. 2 to the 0 is 1. And then 2 to the 1 is 2. 4. 2 to the 3 is 8. 2 to the 4 is 16. Okay, so if you were to look at that, these are all points that exist on the exponential function graph. And we can see that, like if x is equal to 2, y is equal to 4. X is equal to 2, y is equal to 4. What we'll do now is we'll take a look at the inverse, right? So log x base 2. All right. When x is equal to 0, remember, we just said log 0 base 2 does not exist. So when x is equal to 0, there's no value. This does not exist. Then, if we look at the original function right here, remember, this right here is the original exponential function, and this is the inverse. So we said previously, what happens? The x and y values are switched in the inverse function. So to easily get this, I just say, okay, that was the y value. This is now the x, and now that's the y. So that's negative 3. 1 over 4, 1 over 4, negative 2, negative 2. 1 half, 1 half, negative 1, negative 1, 1, 0, 1, 0. Okay. And then I have 1, 2, 3, and 4. So this allows me to plot the logarithmic graph. And so I'll go ahead and do that, and I'm just going to pause the video and get that completed so you can try doing the same. Okay, so I've plotted all my points here, and I have, as you can see, I have the logarithmic graph right here. Okay. And the logarithmic graph does definitely look like a reflection of the exponential graph and the line y equals x. So if I was to draw a line, y equals x right through here, this blue definitely looks like a reflection of the original exponential graph. So this is the inverse of the exponential graph. Again, let's see if we can come up with some key points here. Well, remember our key point on the original exponential graph was 0, 1. So therefore, a key point on the logarithmic graph would be 1, 0, because the logarithmic graph is the inverse of the exponential graph, so we switch the x and y values. We can see right here that the logarithmic graph is strictly increasing as well. So we can write that. That's strictly increasing. We also saw that x can never be equal to 0 because we said there is no exponent on that base that will produce a value of 0. So if x cannot be equal to 0, that means that's a restriction, and therefore we have a vertical asymptote. So we have a vertical asymptote, x is equal to 0. And interestingly enough, remember we had a horizontal asymptote, y is equal to 0. So on the inverse function, we're going to switch x and y, and now it's going to be x is equal to 0. Given that we switch the x's and the y's for the inverse function, you can probably see that the domain is going to be simply the inverse of the original domain. So this would be x is an element of all real numbers such that x has to be greater than 0. And we can see that on the graph. Look, x values can only be positive, and they can't be equal to 0, again, because there is no exponent that produces 0. The range would simply be this value right here. So y is an element of all real numbers. Okay, so you can see that they're switched because it's the inverse, the asymptote switched, the key point is switched. Okay. And that right there concludes the lesson. I think the key thing to really remember, if I was to say remember as much as possible, is this right here. And you can highlight this. That when you do a logarithm, all you're doing is you're giving the exponent on the listed base, that produces the number right there. So here, 3 to the negative 2 produces 1 over 9. So this right here is the exponent on 3 that produces 1 over 9. This is the exponent on 2 that produces 4. This is the exponent on 2 that produced 1. So that is what you really want to be thinking about when you are evaluating logarithms. Thanks for watching.